Good day, class. For today's video, we will be discussing concrete, especially the proportioning of concrete mixes. But what is concrete? Concrete consists of rationally chosen mixture of binding material such as lime or cement, well-graded fine aggregates, coarse aggregates, water, and admixture to produce concrete with special properties. And these are the qualities required of a properly proportioned concrete mixtures. First is accepted workability of freshly mixed concrete, durability, strength, and uniform appearance of hardened concrete, and lastly is economy. And according to ACI, the basic steps for determining mixed design proportions can be defined by absolute volume method. And here are the steps or the procedure for us to determine the mixed design proportion. First is the strength requirement. Next is the water cement ratio, coarse aggregate requirements, air entrainment, workability, water content, cementing material requirements, admixture, fine aggregates, and lastly is the moisture correction. Let us use these requirements or procedures for us to solve this sample problem in designing concrete mix. In this problem, we have to design or create a concrete for bridge which is exposed to freezing and subjected to de-icing chemicals. The required strength here is 24.1 megapascal. The minimum dimension of the pier is 0.3 meter with the minimum space between reinforcing bars is 64 millimeter. The minimum cover is also 64 millimeter. The standard deviation of compressive strength is 2.4 megapascal. And we are expecting that there are 30 samples and we should only allow air entrainer on this design. Next is we have to use type 5 due to exposure cement and an air entrainer with the manufacturer specification of 6.3 milliliters per 1% air per 100 kilogram cement. The coarse aggregate has a 25 millimeter nominal maximum size which is a river gravel round. Bulk oven dry specific gravity is equal to 2.621 with an absorption of 0.4%. The oven dry rodded density is equal to 1,681 kg per cubic meter. Moisture content of 1.5%. For fine aggregates, we will be using here a natural sand with a bulk oven dry specific gravity of 2.572 and an absorption of 0.8%. Moisture content is 4% and fineness modulus is 2.6%. Let's begin with the strength requirements. For the strength requirements, we have a given of standard deviation of compressive strength which is 2.4 megapascal with more than 30 samples. And the required strength is 24.1 megapascal. But this is not the final strength that we are going to use because according to ACI, the required average strength FCR should be used on the design mix proportion. FCR meaning we'll be using this formula for us to solve the required average strength. Using this formula, we have FCR is equal to FC prime plus 1.34S, wherein FCR is the required average compressive strength. This is what we are looking for. And FC is specified compressive strength, which is this one. And S is the standard deviation, which is this one. Substituting the given, we have 24.1 for FC prime and 2.4 for the standard deviation. Solving for FCR will give us 27.316 megapascal. Now, this is not the only formula that the ACI suggesting. We have also here another formula for a large standard deviation. So we'll be using this formula for metric system and substituting the given to the equation. We have FC prime of 24.1, standard deviation of 2.4, and the answer is 26.242. The question is, what is the required average strength shall we use from these two FCR? According to ACI, the required average compressive strength FCR is determined as the larger value obtained from equation 4-1 and equation 4-2. Therefore, we'll be using larger between these two, which is equal to 27.316 megapascal. We already have now our required average compressive strength FCR. Next is water cement ratio requirements. Actually, water cement ratio is needed to produce the required strength FCR, which is what we've solved earlier, which is 27.316. Now, table 4-5 can be used in estimating the water cement ratio for trial mixes with no other data are available. The required average strength, this column, is used with the strength versus the water cement ratio. On the problem, we are allowing an air entrainer. Therefore, we'll be using this column and take note that FCR is 27.316, which is in between 21 and 20. 0.28, which corresponds to 0.48 and 0.59 for an air-entrained concrete. Using the linear interpolation, we'll be solving the water-cement ratio, which is corresponding to 27.316 megapascal of FCR. Now, we have this one, 0.48 minus 0.59 all over 28 minus 21 is equal to X, or the unknown water content, minus 0.59 all over 27.316 minus 21. Therefore, the water content will be equal to 0.491. Now, this is not the final answer for the water-cement ratio because according to ACI, the water-cement ratio required for the strength is checked against the maximum allowable water content given by the table 4.6 and 4.7. And let us try now to compare that on the table 4.6 and 4.7. From table 4.6, for us to determine the maximum water-cement ratio, we have to determine the exposure condition of the concrete that we are going to create. From our problem, the design environment of a bridge is exposed to freezing and subjected to de-icing chemicals. Therefore, going back here on the table 4.6, it is belong to this exposure wherein it is exposed to freezing and thawing in moist condition or de-icer, which corresponds to 0.45 maximum water content. But this is not the only maximum water content that we are looking for. We should also consider this table 4.7 wherein the exposure here are in category moderate, severe, and very severe, which means we have to categorize these exposure conditions. Again, from ACI, mild exposure is corresponding to indoor or outdoor surface in which concrete is not exposed. Moderate exposure, some freezing exposure occurs, while severe exposure, concrete is exposed to the icing, meaning this is the exposure that we are looking for, which is concrete is exposed. And that severe exposure corresponds to 0.45 maximum water content. Now, what if we have different maximum water content here? If that will happen, we have to choose the smaller value between the two. But since they are similar, therefore, the maximum water content is equal to 0.45. Now, we have to check the strength requirement water cement ratio if that exceeds with the maximum. And if that exceeds, we have to select the maximum water cement ratio. Next is coarse aggregate requirements. In this step, we will be finalizing the nominal diameter of coarse aggregate and also the quantity of this coarse aggregate. Now, from the given, we have already the nominal diameter maximum size, which is 25 millimeter. But we have to check this first on the ACI requirements if the maximum allowable size aggregate does not exceed with these following requirements. But we don't have this maximum allowable size. We only have here the nominal maximum size. But remember that the maximum allowable size is one step higher than the nominal maximum size. Therefore, we have 37.5 for the maximum size. If we are going to take a look with these sizes of the aggregates, 37.5 is one step higher than 25, which is the given nominal maximum size. Now, we'll be comparing this first to the 1/5 of the smallest dimension, which is 300, and still 37.5 is less than this one. Next is 3/4 of the minimum clear spacing between reinforcing bars. Still 37.5 is less than this one. And the last is 3/4 again by the reinforcing bar, which is 64, and 37.5 is still less than this one. Therefore, the aggregate size is okay for the dimensions, meaning we are good here in using 25 millimeter nominal maximum size. Once the fineness modulus of the fine aggregates and nominal maximum size of the coarse aggregate are determined, the volume of coarse aggregate per unit volume of concrete is determined using this table. Since we already have the nominal maximum size of 25 and the fineness modulus of 2.6, you just have to plot that on this table with the fineness modulus of 2.6. Therefore, we will be using this 0.69 as a factor of the dry density of the coarse aggregate, which is 1681 kg per cubic meter. Multiplying that factor, we have 1159.89 kilogram per cubic meter of concrete. Next is air entrainment requirements. For this requirement, we just have to take a look with this table 4.9, which is the approximate target percent air content requirements for different nominal maximum size aggregate. And if we are going to recall that we are in a severe exposure wherein concrete is exposed to de-icing salt. Since we have severe exposure, we will be selecting this one in air entrained concrete, which corresponds to 25 millimeter nominal maximum size aggregate aggregate, we have 6% of target air content. And if we're going to take a look with these two asterisks, the air content in job specification should be specified to be delivered within -1 plus 2 percentage point of the target value. Therefore, this 6% should be less by 1%, which is 5, and also should be added by 8%, and we'll be choosing here the larger air content, which is 8%. Next is workability requirements. Workability is defined as the ease of placing, consolidating, and finishing freshly mixed concrete, and concrete should be workable but should not segregate or excessively bleed. In this case, we're just to select the maximum and the minimum slump corresponding to the type of concrete construction. In our problem, we are going to build a pier which best fits as a column. Therefore, selecting these building columns will give us a minimum and maximum slump range, which is 25 to 100 millimeter, and we have to select, of course, the maximum slump, which is 100 millimeter. Next is water content requirements. The water content required for a given slump depends on the nominal maximum size and the shape of the aggregates and whether an air entrained is used. From table 4.11, we can determine the approximate mixing water in kilogram per cubic meter for different slumps and nominal size of aggregate. Since we have 25 millimeter aggregate with air entrainment and 100 millimeters slump, therefore we will be selecting here the air entrained concrete with a 75 to 100 millimeter slump and also the 25 millimeter maximum aggregate size. Therefore, our water now is equal to 175 kilogram per cubic meter of a concrete. Take note, this is for angular. If we're going to take a look with these two asterisks, they are the maximum for reasonably well-shaped angular coarse aggregate. But we have a round coarse aggregate, but the coarse aggregate that we're going to use is a round coarse aggregates. And using this table 4.12, we have to reduce all those other aggregate as shown in this table. Since we have here a round coarse aggregate, we should subtract 27 to 175, which will give us 148 kilogram per cubic meter. And that would be the required water content now. Next is cementing material requirements. Actually, in this step, we are just going to calculate the quantity of cement that we are going to use on the concrete mixture. Since we already have the water cement ratio of 0.45 and the water content of 148 kg per cubic meter, we just have to divide the water by the water cement ratio and will give us the cement of 328.889 kg per cubic meter. But ACI provides minimum requirements for cementing materials, which is shown in this table. We just have to select the nominal maximum size and the corresponding cementing materials. In this case, we have 25 and 310 here for the cementing materials. But if we are going to take a look with these two asterisks here, the cementing materials quantities may need to be greater for severe exposure. Take note, the pier that we are going to build is in severe exposure. Therefore, it should contain at least 335 kg per cubic meter of cement. And that would be our minimum cement requirement. What's next is to check if the cement here passed the requirement. If we're going to take a look, 328.889 is less than the minimum. Therefore, this 335 will be used. And take note that increasing the cement content without increasing water will slightly reduce water-cement ratio, producing a less permeable mix that is good for severe exposure. Next is admixture requirements. If we're going to take a look again with our problem, we're going to use here an air entrainer. And actually, air entrainer is used to achieve a proper air void system or to correct the amount of air and the correct size and spacing of the air bubbles. Now, since air entrainer here uses a manufacturer specification of 6.3 milliliters per 1% of air and per 100 kg of cement, we'll be needing here air content and also the cement requirement. Since we already have 8% of air content that we have calculated, we just have to multiply this air and cement to the manufacturer specification and will give us an answer of this, and that will be our admixture, which is 168.84 milliliters per cubic meter of concrete. Next is fine aggregates requirements and moisture correction. But before we discuss this, let me explain first the absolute volume method. Actually, this method is just getting 1 cubic meter of concrete which contains cement and aggregates in solid state and shall not include the volume of air spaces between its particles. These voids will be filled with water, admixtures, and air. The absolute volume can be computed using this formula. So we have mass of the loose material over the specific gravity times density of water. Now, to understand this absolute volume method, let us take a look with a 1 cubic meter of freshly mixed concrete. This 1 cubic meter of concrete should contain coarse aggregates, fine aggregates, cement, water, air content, and if applicable, it should also contain admixture. And these three should be in solid state, absolute volume, and these three are the voids. Since this concrete contains voids, we can say that this concrete has a loose volume. For us to simplify the solution in calculating the remaining unknowns, which is fine aggregate and water corrections, let us now tabulate this data. The table shall contain ideal quantities, absolute volume considering 1 cubic meter of concrete, moisture corrections, and those are water content and absorption. And finally is the actual quantities that we are going to use in proportioning concrete mixes. Let us put these values on the table. We have coarse aggregates of 1159.89, air content of 8%, water content of 148 kilogram per cubic meter, cement is 335, admixture is 168, and fine aggregates is unknown. Since this fine aggregate is unknown, we have to jump on this absolute volume and computing this absolute volume needing a specific gravity. From the problem, we have a given of specific gravity for coarse aggregate and fine aggregate. And let us use that on this equation. For coarse aggregate, we have 1159.81, which is the mass, over the specific gravity of 2.621 times the density of water, which is 1,000. And that is equal to 0.443 cubic meter of coarse aggregate per 1 cubic meter of freshly mixed concrete. For the air content, that is 8% of the total volume or 0.08. Water is 148 kilogram. Converting that into volume, we have 148 over 1, which is the specific gravity of water, times 1,000. And that is equal to 0.148 cubic meter of water per cubic meter of concrete. For cement, we don't have any specific gravity given on the problem, but it is stated that we should use type 5 of cement, and this type 5 is under on the Portland cement. And from your unit 2, Portland cement has 3.15 specific gravity. Now, we'll be using this 3.15 to compute the volume. We have 335 for the mass over the specific gravity of 3.15 times the density of water, and that is equal to 0.106 cubic meter of cement per cubic meter of freshly mixed concrete. Now, we don't have any data for the admixture, especially the specific gravity, for us to compute its absolute volume. Therefore, we will not include this on calculating the absolute volume. And the only unknown now for the volume is the fine aggregate. For us to compute this fine aggregate, since we are considering a 1 cubic meter of freshly mixed concrete, therefore we just have to subtract all knowns to 1 for us to get this unknown fine aggregate. Now, let's do that. We have 1 minus 0.443 minus 0.08 minus 0.148 minus 0.106, and the fine aggregate now will be equal to 0.223 cubic meter of fine aggregates per 1 cubic meter of freshly mixed concrete. We can now solve for its ideal quantity in kilogram. For us to solve this, we'll be still using this absolute volume formula. We have 0.223, which is the volume, is equal to unknown mass of fine aggregates over the specific gravity of fines, which is given here, times 1,000, and mass now is equal to 573.556 kilogram. Next is moisture corrections, wherein we have to calculate the water content and absorption present in aggregates because the ideal quantities of aggregates are in dry rotted, but in the market, aggregates are in moist condition. Calculating for the water content of coarse aggregate, the moisture content of 1.5% is given. We have to multiply it to the ideal quantity, which is 1159.89 kilogram, giving us the value of 17.398 kilogram. This water content is to be added to the ideal quantity of coarse aggregate to get the actual quantity. Thus, 1159.89 plus 17.398 is equal to 117.288 kilogram. Then, for the water content of fine aggregates, moisture of per percent to be multiplied to 573.556 and will give us 22.942 kilogram. The actual quantity will be 573.556 plus 22.942, and that is equal to 596.498 kilogram. Now, this water content present in the aggregates will be subtracted to the amount of water calculated, which is 148, to prevent the concrete bleeding or applying excessive water. Thus, we have 148 minus 17.398 minus 22.942. This equation is not yet final. Take note that the aggregates can absorb water for the percentages given in the problem. Thus, this must be also considered by adding the absorption content to the water. Calculating for the absorption content of coarse aggregate, we have 1,159.89 times the absorption of 0.4%, we have 4.64 kilogram. While for fine aggregates, 573.556 times the absorption of 0.8, and that is equal to 4.588 kilogram. These two quantities will be added to the water for concrete mix. Thus, we have here 4.64 plus 4.588, and the actual quantity now of the water is equal to 116.888 kilogram of water. And for the cement, this 335 will not change, giving us the actual quantity of 335. And for the admixture, still 168.84. And for the summary, we have this batch ingredient required. For the water, we have 116.887 kilogram, cement of 335 kilogram, fine aggregate of 596.498 kilogram, coarse aggregate of 1,177.288 kilogram, add mixture of 168.84 milliliters. And take note that this quantity is for 1 cubic meter of concrete. And this is our final answer.